Starting with 5A. So we are given the rate of change of the number of mosquitoes on some tropical island at time t days. We're given this function in mosquitoes per day, and we're told that there are initially 1,000 mosquitoes. This is a calculator question. Right? So part A says show that the number of mosquitoes on tropical island is increasing at t = 6. Well, increasing is dealing with the rate. Okay? We want to show the rate is increasing. What that means is we want to show that the derivative function, which, we're thinking about this as the derivative. This is the rate of change function. We just want to show that that is positive at 6. So all I would do is plug 6 into this function and show that I get a positive value. And this is calculator active. So we would just say m of 6 equals 5 times the square root of 6 times the cosine of 6 over 5. Plug that into the calculator. We should get a positive value. What do we get? 4.43. Okay, so this is the rate. So at 6, or at time t = 6, we would say the rate at which this is changing is 4.43 mosquitoes per day. The rate at which mosquitoes are, or the population of mosquitoes is increasing because the rate is positive.
I did this wonky, and I probably would have hit points, but I could show the list.
Probably not. Alright, then B, set up an integral to determine the net change in the mosquito population on the island for t is between 0 and 31. How would I do this?
This is the 1 over the 2, like 31 minus 0.
No, it's not asking for the average. That's when we're asked for the average value. Yeah, right? We're just going to set up our integral from 0 to 31 of my rate function. So 5 times the square root of t times the cosine of t over 5 dt. Make sure when you're setting up your integral you have dt in there. So is that going to be... Yeah, so that's going to be the net change on the island. We just plug this into the calculator. What do we get? Negative 36. Okay, and it does say round your answer to the nearest whole number. So the net change in mosquitoes is down to 36. We have 36 fewer mosquitoes on day 31 than we did on day 0. So now, part C says, how many mosquitoes will we actually have? This year?
Yeah, I mean,
Oh, yeah. Yeah, that works. Yeah, so in part B, we found the net change, right? So we're just saying we started with 1,000 mosquitoes. Over the course of 31 days, we lost 36 mosquitoes. So we would say 1,000 minus 36 equals 964 mosquitoes. Yeah. You okay with that one? Okay, and this is that idea of initial value plus net change equals final value. Okay, we started with 1,000. Our net change was negative 36, so our final value is 964. Good with that one? What else? Eight? Sure. Somebody say 6? No?
Yeah, I did.
Okay. So
I didn't do it.
Like I wrote down an equation for that.
So do you want to?
Yeah.
Okay. So on this one, we are told the linear density of a rod of length 4 meters is given by this function, measured in kilograms per meter. So this is essentially a rate function. Kilograms per meter is a rate. It's really a density, but for our purposes, we're considering it a rate. So we want to set up an integral to find the total mass in kilograms of the rod. So if I integrate my density function, which is kilograms per meter, I will get kilograms. So it says that, let's see, this is a 4 meter long rod. So I'm going to be integrating from 0 meters to 4 meters of my density function. 9 plus 2 times the square root of x. Make sure when you're setting up your integral, you have dx on there. So this one, it does say to do by hand. Right? You do this without the calculator. So to do that, I would take the antiderivative of each of these pieces. The antiderivative of 9 would be 9x. The antiderivative of 2x to the 1/2, well, I would add 1 to the exponent. So that would be x to the 3/2. Then I take the old coefficient over the new exponent. So 2 over 3/2. Well, that would be the same as 2 times 2/3, right? Which would be 4/3. So my coefficient here would be 4/3. And then I'm evaluating this from 0 to 4. So I'm doing f of 4 minus f of 0. So this will be 9 times 4 plus 4/3 times 4 to the 3/2 minus
0.
Yeah, all of this will end up being 0. But I'm still going to write it out and show it. Okay, and if this is a free response question, stop there. Okay. Technically, this isn't too bad to evaluate by hand if we wanted to actually get a number. I mean, something like this could be a multiple choice question. Right? I mean, this is short enough that this could be a multiple choice question where we would actually have to evaluate this by hand. So let's go ahead and do that real quick. So this would be 36 plus 4 to the 3/2 power. How do I do that part?
The square root of 4 to the 3rd.
Right, the square root of 4 to the 3rd power. So the square root of 4 is 2. 2 to the 3rd power is 8. So 4 to the 3/2 power would be 8. Then 8 times 4/3 would be 32/3. Then if I wanted to combine this into one number, I would need to get common denominators. So 36 I would need to turn into thirds. So multiplying that by 3 would be 108. So 108 thirds plus 32 thirds equals 140 thirds.
Can you go over the process of
So yeah, so whenever I have a fractional exponent, the denominator of the exponent tells me what root to take. So this is really the same as the square root of 4 to the 3rd power, which would be 2 to the 3rd, which would be 8. You okay with that one? Then number 8, somebody said.
please help with me?
Alright, so the marginal cost of manufacturing X yards of a certain fabric is given by this function, which is in dollars per yard. We want to set up an integral to determine the increase in cost if the production level is raised from 2,000 yards to 4,000 yards. So my variable is in yards. Okay? If I integrate this function, which is in dollars per yard, I will get dollars. So what I want to do is integrate this function from 2,000 to 4,000. Okay, I'm saying I'm increasing the number of yards from 2,000 to 4,000. And let's see, 3 minus 0.01x plus 2, 3, 4, 5 zeros. 6 x squared dx. Okay, so this would be my setup. And then we can just plug that whole thing into the calculator. So what do we get when we plug that into the calculator? What is it? 58,000? $58,000 even?
Yeah.
Nice. Alright. You okay with that one? What else? 10C. Good on A and B?
Yay.
Okay, so part B says we want to use a left Riemann sum with 5 sub intervals, and then part C asks, is that an overestimate or underestimate? So if I'm setting up a left Riemann sum, left means I'm taking the height from my left endpoint, right? So my first rectangle would be from 0 to 30. Its height comes from the left endpoint. Then for 30 to 40, the height of this rectangle, if I'm using a left sum, comes from the left endpoint. We would continue in that manner, right? So this is what my sum would look like. 70. So is that an overestimate or an underestimate? Under, right? Now, I think it did ask to explain why, right? Yeah, justify your answer. So what would be a good justification for why this is an underestimate? We actually only need to say it's increasing. For rectangular approximations, all we're caring about is whether the function is increasing or decreasing. So since it's increasing, and we're using a left sum, we say that it's an underestimate. For trapezoidal sums is where we talked about concavity. And if it was concave up, a trapezoidal sum would overestimate. If it's concave down, a trapezoidal sum would underestimate.
So if it was decreasing the left Riemann sum would be overestimated.
Right. Yeah, so I mean we can just sketch out an example. Say, I guess that's not all increasing. There we go. So if we take a rectangle from here to here, and take the point on the left, that's an overestimate, right? And I mean, even on the test, right? You can sketch that out if you don't just remember that. You can say, well, I need to draw a picture. Let me draw a decreasing function. If I draw a left sum, that's over the curve. If I draw a right sum, it's under the curve. You okay with that one? What else? Nothing else? All right, then today we're going to take a look at how this has shown up on the AP test the last 4 years. Okay, there's a pretty specific type of question that has shown up on the AP test the last 4 years. And these are those 4 examples, 2015, 16, 17, and 18. Alright. Yeah, a lot of people won't be here for that. Hopefully I'll have it ready tomorrow.
David. Malone. Oh yeah. I don't
Alright, so each of the last 4 years, a problem like this has shown up on the AP test, where we have two rate functions. Okay, a rate modeling something going in and a rate modeling something going out. Okay, in this problem, we're talking about rainwater flowing into a drain pipe. Okay, so we've got this function, R of t, is the rate at which water flows into this drain pipe. But then we have another function, d of t. This is the rate at which water is flowing out of the drain pipe. Okay? This in and out problem has been very, very common on the AP test. So it's pretty safe to guess that something like this problem, okay, like these 4 problems that we've got here in front of us, is going to show up on the AP test. Okay, so part A for this problem says how many cubic feet of rainwater flow into the pipe during the 8-hour time interval, 0 to 8. How would I set up, how would I solve this? What do I need to do? This is a calculator problem, yes.
So we just plug in 8 into the
Plug 8 into what? We have to do the integral. Right? If I just plug 8 in, that will get me the rate at which water is flowing at that specific moment. Right? Yeah, so I'm going to say the integral from 0 to 8 of, am I just doing R of t or some combination of R and t and d and t?
No, it's just R.
Just R of t, right? Because all we're talking about is water flowing into the pipe for part A. So I would say the integral from 0 to 8 of 20 times the sine of t squared over 35 dt. That we can just plug into the calculator, right? Math 9. Plug that whole thing in. What should I make sure of though before I plug stuff in?
Oh, you're in the right.
Right. We're dealing with a trig function, so we need to make sure we're in radian mode. So what do we get if we plug that in? 76.5703. Alright. So remember, always go to 3 decimal places. Now what would my units be?
Cubic feet.
Cubic feet. Cubic feet of rainwater. So that's how much has flowed into the pipe during the first 8 hours. Okay, so far? Part B then says, is the amount of water in the pipe increasing or decreasing at 3 hours? So I've got a function modeling water flowing in, function modeling water flowing out. How would I figure out if the total amount of water is increasing or decreasing at 3 hours?
Do you do the integral of both of them? And then you subtract the one.
Don't you just
Obviously, that's wrong.
positive and negative?
Yeah, so we just want to plug 3 into the functions that we have, not into the integral. Because what I want to figure out here is whether I'm increasing or decreasing, not what the total amount is. So here, for part B, we would say, well, R of, we actually want to see what R of 3 minus D of 3 is, the rate at which water is flowing in minus the rate at which water is flowing out. So R of 3 minus D of 3 would be 20 times the sine of 3 squared over 35 minus, we have negative 0.04 times 3 cubed plus 0.4 times 3 squared plus 0.96 times 3. So what do we get if we plug all that into the calculator? It's a positive number? But this could be a negative. So let's do it. Let's evaluate this. Remember, make sure you're in radian mode. I guess I should have had parentheses around all that.
Positive 10, maybe.
I got 8.
I get 12.64.
I got negative 0.31.
What?
That's really good. So I'm guessing the mistake that a lot of people made was not having parentheses around this. Right, so I'm taking R of 3 minus D of 3. I'm subtracting this whole thing. Right, so to show that I'm subtracting this whole thing, that would need to be in parentheses.
Wait, so what did you get for like the? Did you shoot all?
I just did it all in one thing.
Yeah, I might have put 25, not 23. Me. Yeah, 25, not 35. I wasn't joking. We all hate each other here.
I don't think that's true. I
I
said I don't think that's true.
Smart. You always do it.
You call yourself an idiot.
Alright, so what does this mean then? How do I answer the question?
There's more water going out of the pipe than more water goes into the pipe.
Right. Okay, since I got a negative value here, I would say that the amount of water in the pipe is decreasing at 3 hours because R of 3 minus D of 3 is a negative number.
Woo.
And we would need to write that out. Okay, I'm not going to write that out here on the board. I'd say it's decreasing because R of 3 minus D of 3, which is the rate at which water is flowing in minus the rate at which water is flowing out, is negative. You okay? Alright, C then says at what time between 0 and 8 is the amount of water in the pipe at a minimum?
At 2 hours.
How'd you get that?
9 hours.
How would we figure this out? How would I figure out where the amount of water in the pipe is a minimum?
Find places where both of equals 0.
Yeah, well, we want to set the rate equal to 0. Well, whenever we're finding maxes or mins, we want to find critical values, right? Critical values are where the derivative, which the derivative is the rate function, equals 0. We're given the rate functions. So, yeah, so how would I do that? Which one or one, should I combine them? Should I set them both equal to 0? What should I do here?
Multiply them? You eat them?
Just the R one?
Well, since the R one is positive,
She said
so it has to be R equal.
I don't want to set them equal to 0 separately.
I said.
So should we add them? Should we subtract them? Divide or multiply?
You said them equal to each other.
Use substitution.
Take the derivative. No, not the derivative.
We're all gonna fail this.
When in doubt, take the derivative, right?
Yeah.
I'm not going to subtract.
I hate that I'm not even joking. I have no idea about that.
Take the integral. We'll just
So if this is the rate at which water is flowing in, and this is the rate at which water is flowing out,
And we want min. We want RT 0.
Alright,
Stop
we
finishing
subtract
the
them,
sentences.
and then set that equal to 0.
I'm
Yes.
trying.
My final verdict.
Please talk.
you are correct.
It makes sense.
Okay. So what we want to do, the function that would model the amount of water, or the rate at which water is coming into the tank is R of t minus d of t, right? So I want to set that equal to 0. So I'm going to say 20 sine of t squared over 35 minus, and again, make sure we're using parentheses, negative 0.04 t cubed plus 0.4 t squared plus 0.96 t. What would the best way to solve this with a calculator be?
Graph it.
Right. And that's going to be the easiest way.
Hey.
You're not using
You need to tell your calculator, by the way.
Well,
You charge them.
yeah, these aren't charged.
She wasn't going to use it anyways. You see her.
Let me just know what I need.
Just see. Well, so our x values that we care about are 0 to 8. Right? So making your x window 0 to 8 would probably make sense. So where on the interval 0 to 8 does this function r of t minus d of t equal 0? It is close to that. How would you figure that out exactly? We want the 0 So
No, it's second how.
yeah, so we would do second trace, and then the second option is 0. Oh, because you said in 0 axis, which should be fine.
Oh, I don't do it.
Sure. So problems would make our window a lot smaller. So what do we get for the values at which 3 point, say it again?
3.27.
Oh, 3.2716.
Wait, so do we get the minimum and then go to the bottom of it?
We want to find where it equals 0.
Oh, it's just the x-axis.
Yeah, where it crosses the x-axis.
Okay. I'm having. Because you said it was why.
I don't know. I mean, that's,
Okay.
you can just kind of guess and check until you find a good window.
And then you do second.
Oh, you graphed both of them individually? Okay. So, yeah, I mean, if you're doing that, you're finding where they intersect.
Okay. That's why I was confused.
So did we get 3.2716? So we want to figure out if that is a minimum. Okay. I guess is it going from positive to negative or negative to positive? Negative to positive. So does that mean it is a relative min or max? Min, right? If it's going from a negative slope to a positive slope, that would be a min. So, let's see, does it ask? No, it doesn't even ask for what the value is.
Yep, froze.
Turn it on. Check the batteries.
So, what would our justification be here for that this is our minimum?
Plus it goes from negative to positive.
What goes from negative to positive?
The slope.
So we could say that the rate of change, or R of t minus d of t, changes from negative to positive at this value. Therefore, it is a minimum. Okay, then part D, the pipe can hold 50 cubic feet of water before overflowing. For t greater than 8, so everything we've done so far has been on this interval, right, 0 to 8. So now it says for everything greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe overflows. Write, but do not solve, an equation involving one or more integrals that gives the time when the pipe will begin to overflow. So, as we get into the final few things that we're going to do, we're going to see more and more things that say this, like set up an equation or set up an integral, but do not solve it. Okay? So how would I set this up? Okay, how can I figure out when this pipe would overflow? Well, yeah, so what we're going to set something equal to 50. What am I going to set equal to 50?
Is it this RT minus DR?
that'll be part of it. But we also have to account for the water coming out as well, right? So there's some water coming in, some water coming out, and I want to know when that total is going to get over 50. So what I'm trying to figure out is the total amount of water, right? So if I'm given the rates, to get the total amount, I would have to take the antiderivative or integrate, right? So I know I'm going to somehow have to have the integral of my rates, r of t minus d of t dt. Now, one piece that we haven't used yet, we are told that at the start, at t equals 0, there are already 30 cubic feet of water. How would I take that into account here? Yeah, should we add it or subtract it here? Add, right? That's the initial value. So initial value plus net change. We want to figure out when that equals 50. Now, my bounds on my integral. I know I'm starting at t equals 0. Right? My upper bound is what I'm actually trying to solve for. Right? I'm trying to solve for this time. The time when my initial value plus the net change equals 50.
So is that our x?
So that is my variable, the upper bound on this integral. So this is the entire answer to part D. I don't have to solve it. I don't have to try to do anything. Okay? I just need to set up this integral. So that's just the answer. You okay with that? I was hoping to get through 2 of these today. Obviously, we only got through 1. You guys feel like you can try 1 or 2 of these for homework?
Maybe.
All right, let's see. How about